recording. All right, so as Harry mentioned, this topic, I think, came out of a conversation that we were having on the repeater, and I think it was in response to a Tuesday Night Net. I believe that the topic of the evening was whether or not any of the participants had played with any of the digital voice modes available to amateurs. And by and large, most people said no. Some people had some experience with a few of the modes, including DMR, which is the mode that Mark's going to speak about tonight. But most people didn't. After the session, Mark piped up and noted that he had done some of the fundamental work on digital mobile radio, or what we know of as DMR, and that he might be interested in giving a presentation to the club about some of its technical workings. I kind of goaded him on and talked him into it and gave him a whole bunch of homework, and he's come through and put together a presentation this evening, which he assures me is not an exhaustive explanation of the technical aspects of DMR, as that would take, an entire university course to explain, but more of a technical overview of the protocol. So I'm really looking forward to this. So please welcome our very own Mark VE3QAM to tell us about digital mobile radio. Mark, go ahead, take it away.
Hello, let me bring up my screen here. Let's see, there we go. So, yeah, originally I talked with Jonathan about this. He was more curious about the radio aspects, and I was thinking about it. And I realized that most of the DMR presentations that you'll see on YouTube or articles that you read are more about the networking aspects. And my experience was really with the radio stuff. I didn't work on DMR. I worked on GSM and GPRS and 3G and 4G cellular. But DMR is based on Tetra, which is based on GSM. So a lot of it's the same. It's the same stuff. It's just DMR is sort of a Tetra Lite or something like that. So I want to actually talk more about the radio stack, because not just because you don't really hear it very, very often, but because there's more and more digital radio these days in ham radio, and you'll see this more and more, and it works vastly different than analog stuff. So let's see, how's this? There we go. I just figured out how to advance the slide here. So what we'll talk about is the system architecture, how it differs from FM communications. We'll talk about parts of the stack, what's different about it, what do we do to send and receive digital information, digital voice in particular, DMR radio stack architecture, and we'll trace a little bit of a signal through the stack. This will be like 40 minutes. It's not very long, so we're not going to go too deep, but we'll show you some things, radio resource management, and this is stuff that you should know, because that doesn't exist on FM or any analog mode, nor does the addressing scheme. So DMR is an ETSI standard. It's an open standard of the European Telecommunications Standards Institute, located in Sofia Antipolis. It's the same standards body that brought us GSM, 3GPP, which is 3GPP is a project of ETSI and a bunch of members. 3G, 4G, 5G wireless. It's a member-driven open standard. So in other words, you can download whatever standards you want from ETSI. They're free. Just be sure when you do it, you want the right date, because they change all the time. And you can build equipment with it. But if you don't like the way the equipment works with the standard, you need to buy a membership to ETSI. I'm still a member, or my little company is a member. I was just in an ETSI meeting this morning, early. And France is 6 hours ahead of us here. Then if you are a member of ETSI then, or 3GPP, you can certainly bring in contributions, bring a paper in to describe what you'd like to do. And you have peer review. You've got all the insiders in the industry who do this stuff sitting in the room with you. And that's how it works. So DMR standards are based on this 102.361 series. Now these are TSs, technical specifications. Technical specifications use normative language. They should, shall, may, must type language. It's almost a bit of a legal thing. If you get used to writing it, you're used to reading it. It's not hard, but after all these years, but if I were you and you're not familiar with it, I would start with this TR at the bottom. This technical report is a TR. It uses informative language, 102.398, and it's a summary of what you see in the 361, 102.361-1, 2, 3, and 4. So DMR is, it enables a networked repeater architecture, and you can see each one of these little repeaters that you see around here. This is a diagram I got from Dave Hull's presentation, and each one of these is a separate repeater. They're connected through the cloud, and they're directed by these servers down here. If you can see, this is Brandmeister example, and it shows the 3 US servers or 3 US servers. There's dozens of these things around the world. And so these calls are set up to the talk groups via these servers, and they're directed to the repeaters that carry those talk groups, which we'll see what those are later. They're just identities. And one of the questions that came up, I think this diagram is a good one, because one of the questions that always comes up amongst new DMR users is okay, I'm on time slot 1. How come you're hearing me on time slot 2? And the answer to that is the time slot abstraction is only unique to your repeater. It has nothing to do with anybody else's repeater. So if you're talking, and you can see this here, if you see this guy on the right, lower right repeater here in Livermore 31066, he's on time slot 1. This is being directed over to this other repeater in Otay, and it's coming out on time slot 2 on the same talk group. So there you go. So DMR is a slotted protocol. And so what happens here is there's 2 time slots. Each time slot commandeers the entire radio resource, the entire radio channel for half the time, or roughly half the time. It's actually a little bit less than half the time, but you'll see why. So what you have is user 1, user 2, time slot 1, time slot 2. They just keep repeating. It's 33 and a third times per second. So each user is transmitting or receiving 16, a little more than 16 times per second. And if you see on the right-hand side, this one analog channel can occupy the 12.5 kilohertz spectral occupation in the RF domain. That same channel can carry 2 DMR calls in the same exact spectral occupation. So it's much more. Oops, there we go. So in wireless, capacity is everything. Why is that? It's because it's expensive. Radio spectrum is extremely expensive. And you can, every now and then, there's some auctions you hear about when the ITU releases certain bands around the world. The regulators in the respective countries start to auction off spectrum and raise some cash that way. The other thing is that refarming spectrum is next to impossible. It's not impossible completely, but it may take you 50 years. It has actually, in the US, there was a case where it took more than 50 years to refarm certain spectrum right around 700 megahertz, simply because they couldn't get all the users out of it. And once you sell equipment, it's hard to deal with. So capacity is extremely important to everybody, including hams. And you'll see on the top a DMR repeater that can handle 2 voice channels. Really, all it really requires is a repeater and a duplexer. On the bottom, a normal FM repeater requires a little bit more than twice as much equipment, because you need a combiner, and then you need some PAs, 2 amps that can make up the loss for that combiner, and then you need a multi-coupler, and you probably need right in here, you probably need a couple preamps here as well. But anyway, DMR is pretty efficient and pretty cheap, and it doesn't take up that much rack space in a cabinet that are already overcrowded in most cases. Now, DMR sounds a bit strange compared to FM. It's nominally not as intelligible as FM under excellent conditions. So if you're talking about signals that are minus 70 dBm or minus 60, something higher than that, FM sounds better. But over a fading channel, like a radio fading channel that's time varying over a period of seconds or less, you're popping up and down by 20, 30 dB, and you're going to be fading down to minus 70. You'll be down minus 7. You'll be down at minus 105. Then you'll be popping back up to minus 80. And you'll be popping holes in the transmission. DMR is designed so that it basically, because it is digital, and because of the forward error correction, and because of the combination of the voice coding technique and the channel coding technique, it stays pretty consistent until it completely just goes out. So it sounds pretty much the same until it goes to 0. And when does it go to 0? At about 2% bit error rate. These codecs are designed for about that. Same thing with cellular. The codecs are pretty similar. So under normal conditions, DMR just works generally better. So to show you a little bit about, before we get into the stack, these are the parts of a digital transmitter, a digital voice transmitter. And I got this again from a presentation from Dave Hull. And you can see on top of a plain ordinary FM analog transmitter where you've got the microphone connected to a speech amplifier, signal conditioning, as he's calling it, or some filtering and maybe some compression or something. And that goes into an FM modulator, which could be a phase modulator or a direct FM modulator. By the way, there is a difference between the two. When you have a reactance type modulator, you get a natural 6 dB per octave pre-emphasis that you don't get when you're modulating the oscillator directly. So there is some slight difference there. But in the digital domain, you don't do that. You don't connect the audio right to the phase modulator or frequency modulator. You connect it to a A to D converter. You got this analog varying voltage here. It goes into an A to D converter. This quantizes the signal, and it chops it up and gives you quanta that are 16 bits and a rate of 128 kilobits per second. Now, what does this mean? 16 bits, 2 to the 16 is 65,536. Log base 10 of that times 10 is 48 dB. So your dynamic range is 48 dB. But your quantized speech, digital speech samples are coming up pretty rapidly. You can't really modulate a transmitter directly like that efficiently. So you could. You might occupy quite a bit of the band, or maybe a couple of bands that you don't want to occupy. So you feed it into a voice coder, a vocoder. So the vocoder used in DMR is an AMBE plus, AMBE plus version 2 these days. And what it does the same thing that a vocoder on cellular does. It takes speech samples, digital speech samples, and converts it to not to compress speech samples. It compresses it. It compresses the data, but it outputs two things: filter coefficients and excitation parameters. So in other words, it's outputting something that the decoder could decode, and it's designed to code speech, just speech. Different languages is not a problem generally, but just speech. So if you ever hear, and a single voice, by the way, and DMR is no different. The AMBE Plus is no different than what we did with the ones for cellular. That's multi-rate encoding. So if you ever like have noise in the background of a transmission, it's pretty tolerant to background noise, unless it's somebody else talking in the background. Then you'll hear this unintelligible stuff, and that's why. It's because it's trying to encode a single voice, and it's being interfered with by multiple voices. Now, if you take a look and you see what's coming out is 3.6 kilobits per second out of that vocoder. And if you make the calculation, it's slightly less than 3% of what went into it in terms of the bandwidth. So it really squeezed the stuff down. From there, the vocoder data go to this thing he's calling a framer here, but what it really is doing, it's doing many things. It's putting the speech frames together. It's adding the synchronization frames that go in the middle of it, which you'll see. It'll add the user IDs, the destination IDs. There may be some data as well that's non-speech. And you come up with this packet stream that's actually a bunch of bursts. So it takes the frames and breaks them into bursts. Bursts are the things that go across, they occupy 27.5 milliseconds in that 30 millisecond space of your slot. So you go from there to the modulation formatter, and that gives you an M level, or in the case of DMR, a 4 level square wave. And then you hit this RRC filter. We've used these things many times in the industry, the root raised cosine filter. And that shapes the stuff up, and out comes 4 level pulse amplitude modulation. That's the stuff that's fed to your 4 level FM modulator. And out the antenna it goes. So this is just the basic stuff. And most of your FM, I mean your digital voice techniques, whether it's DMR or D-Star or whatever, most of the stuff looks like this. On the receive side, excuse me, the opposite happens. You receive the signal, you demodulate it with a discriminator or like a phase lock loop. That your demodulated signal is the error voltage. Or discriminator takes the FM, converts it to AM, and then you can actually hear that as time varying audio. In this case, you get 4 level pulse amplitude modulation. You stick it through the match filter. That's what's matched about it is the impulse response of that filter. Just picks it up, and out pops pulse amplitude modulated signals. You recover the clock and the data. So now you're using it as a reference. You've synchronized on it, on your receiver has synchronized on it. And a packet stream comes out. It comes into what he's calling is a deframer. This is RLC, the radio link controller layer 2. And it actually is a demultiplexer, which you can see some of the data can go to where it says data to microcontroller. That's your ID information, all the stuff that isn't speech. It could be signaling packets, it could be signaling data, it could be your user ID, it could be your destination code, it could be whatever. But out of the deframer would come your data stream and sync that goes into the vocoder. So these are again those filter coefficients and excitation parameters that feed into the vocoder, and they turn back into what sounds like speech. It isn't quantized speech, it's synthesized speech, which is why it sounds slightly synthesized. It's not real speech. These speech samples are now converted from digital to analog, and now you get a time varying voltage that you can amplify and come out the speaker with it. So that's kind of how this works. And you'll see this is a common theme over and over and over. And so here is the radio stack. Now the picture on the right, I pulled it right out of 102.361-1. And what I did is I drew these little bubbles on the left side of it so you can see what happens in each of the layers. Now below the radio stack, so you got RF hardware here. Logically below right here is your antenna. That of course feeds the signal into the RF hardware, the receiver, which if you want to trace a signal up the stack, your signal is received, it goes into the physical layer, it's demodulated. The frequency and symbol synchronization is accomplished right there. You synchronize on the arrival times of the bursts, and position your reception in the middle of the frame. And then you pass those bursts up. There's a little queue that pass them up to this data link layer here. This is layer 2 part. In there is, of course, RLC, radio link control processing. You've got channel coding, interleaving radio resource management, or RRM or RRC, as some may call it. There's retry and acknowledgement in the case of the non-speech stuff. The speech you don't do retry and acknowledgement on. Bit ordering. There's medium access control, which I'll show you, which you don't have on analog. And what would happen here is you'd go, this puts the bursts together, figures out what they are, if they're controlled data, if they're controlled packets or call controlled data, they go up this path. So user IDs, short message service, all that stuff goes up here. If they're vocoder packets, they go up here. Your vocoder lives up here. That's where your voice encoder or decoder, all of the voice payload and stuff comes out here and in here. And on the transmit side, the same thing happens. You set up your call with this stuff. You set your destination ID. It's mixed in with a series of voice packets. These things are converted into bursts and they go out. So that is basically how it works. And you can see the abstraction of right here. You can, let's say you have an IP datagram, a UDP packet probably in most cases, and it's broken up into fragments, and those are broken up into smaller blocks with headers for a number of blocks, and then those are broken up into bursts, and so your bursts are going across the time slots. And so if you're this user, you are on time slot 1. So you got time slot 1, another user, time slot 1, time slot 2 is another user, and so on and so forth. You're sharing the whole resource for just part of the time. So your TDMA frame, what does this look like? The base station transmitter transmits the stuff on the top. You'll see it's transmitting something between these time slots. It's the common announcement channel, the catch, as they call it. And every now and then it sends a sync channel, some embedded signaling, some stuff for housekeeping. These are happening, of course, every 27.5 milliseconds, every 30 milliseconds is the period. So TDMA frame is here. This is 60 milliseconds. It's 2 of these things, which could be 2 users. Closer look at this Databurst. This is a generic Databurst. Show you what a voice one looks like and a data one looks like in a second. But What's in the middle is 48 bits. And what's that's used for is mostly the sync information and or embedded signaling. So there's some signaling in there. And what this sync information is about is there's a known sequence, and it's in the standard, it's in the specifications. What the receiver of this burst does is it receives a burst, it looks for this thing in the middle, and it looks at what did it receive in the middle of this burst according to the times it's received, and what is supposed to be there. What am I supposed to receive? What is the sync sequence supposed to be? It takes that, squares them up, because you don't want to go negative on it. And it computes a set of filter coefficients for the receiver so that it minimizes the mean squared difference between what you get and what you're supposed to get. And you hope that the payload in time, temporally to the left and right of this thing, is going to be received correctly. And most of the time it is, but that's what that's for. And it's also can be used for interference cancellation. So you find there's a lot less interference on DMR because of that. So 2 bursts is 1 TDMA frame. That's so you got user 1, user 2, user 1, user 2. So you've got time slot 1, time slot 2. That 2.5 millisecond thing, it's pretty big. There's some guard times on other protocols, but you wonder why is it so big? It's because it carries the catch. It carries a common announcement channel, which has to be used by the mobile to give it access. And there it is. There is a catch. Again, this is what the base station transmits, because unlike your FM or sideband or any other AM, like AM or any sort of analog transmission technique, you don't have the right to transmit. Your mobile is under the base station's control. It's under the repeater's control. So the common announcement channel is the thing that gives you the right to transmit, and it keeps happening over and over and over. The voice burst looks like this. So you can see your color code is up here. So you got that color code. There's four bits of stuff. So it's from 0 to 15. You got a protocol indicator that indicates whether it's a data packet or a signaling, or a voice packet or a signaling packet. You got some link control stuff here that tells it if it's the whole thing might be a link control, a signaling sequence in this middle part here. And then of course you got the embedded parity that controls this whole thing here, and you've got 108 bits on either side for the voice packet, for the voice data. For the Databurst is different. They've stolen another 20 octets off of this, or bits rather, off of this thing. You've got 98 bits on either side. And here you got the color code, the data type, you got the parity, FEC parity here. There's a little more protection because you don't want your signal stuff to disappear. You're signaling, by the way, on all these protocols. Typically is much more robustly coded than the voice. So because if the signaling goes away, the call's gone, So they make sure that it's not going to drop. The voice will drop before the signaling. And in the case of like, you'll notice this in cellular, of course. So this is a demonstration here of how access control works, the medium access controller. It's really different. You don't have this with FM, and this is only true if you're on a repeater. It's not necessarily true if you're on simplex DMR. And I don't have my simplex DMR, my transceiver is set up to be polite, to where if there is something on the frequency, any energy at all, don't transmit. you can do that. The problem is if you get a birdie or some interference from somebody, now you're stuck with not being able to transmit. The repeaters are much smarter than that. You can only transmit if you've successfully received a catch burst, decoded it, and you decoded that message that says you have the right to transmit in the next burst. So here's what happens. Every time you push the push-to-talk switch, the mobile sends a RACH burst, random access channel burst, to request permission to transmit. The base station resource control, the RRC or RRM module, synchronizes with the mobile. It checks the radio resources and the time slot status. And if it's synchronized, and if the radio resource is available, if the time slot's not in use, and the BER is within target, in other words, if it's acceptably, the bit errors are low enough to where it's usable, and it's going to send you a permission to transmit in the catch, the common announcement channel to the mobile station. And immediately right after that, the mobile or your portable will transmit 30 milliseconds of stuff, and then it stops. And it allows the other time slot to transmit, and it receives another catch burst that allows it, that gives it the right to transmit again. And if it indeed transmits again, it triggers another catch burst. If it stops transmitting, then the base station stops sending it the right to transmit. But that's what happens. And so you'll never hear people doubling on DMR through a repeater like that. What happens if you hit your push to talk, you'll get this, they'll get a tone and the screen will say channel busy or something of the sort. So that's, this is something you don't have on FM. And another thing is what goes out on the RF channel. This is your DMR emission mask. So what goes out on the RF channel is way different than FM because you're turning the transmitter on and off 16.6 times every second. And you can see this emission mask, you're starting down here. So you're minimum minus 57 dB below, or minus 57 dB below the nominal signal level. When you, let's say this zero here, nominal is 4 watts with your portable, and then instantaneously for a couple hundred microseconds, you're transmitting 8 watts. And then it settles down through the duration of the usable part of the slot center, and then it shuts off. So what does this mean to you as a user? It also means that if you ever want to measure your frequency or your power output, frequency counter is not going to work, and your power meter is not going to work unless it's a special DMR test set. Now, what we normally do, what Motorola does, you can certainly take your oscilloscope if it's fast enough and measure the power across a dummy load resistor and compute how much power you got. Look at the voltage across the resistor. Or what you normally do in the commercial world is the Motorola turbo tuner that you connect to your transceiver. It just puts it into the FM mode and transmits a carrier, and then you can measure your power output. But don't let this confuse you when you're trying to measure your power output of your DMR handy talkie or mobile or whatever, because it's transmitting and receiving really, really quickly. Now, another thing that's different between analog and digital, and this is the last thing I want to get into here, is the identities and talk groups. And these identities and talk groups are simply addresses Now I know they're bound, like, you know, you'll see Brandmeister or DMR Mark, or there's a bunch of different networks. They have these things they call, okay, here's the Canada talk group, and here's the Geneva, Switzerland talk group, or Swiss Romand or whatever. They're only a suggestion. They have nothing to do with the location. They're not officially linked to that location. They're just addresses. That's all they are. They're 24-bit addresses. So 2 to the 24 equals hex FF, 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 3 FFs, or decimal 16,777,215 decimal addresses. So it's a lot of addresses you got. And you can do a lot of stuff with these things. So what's the difference between a individual address and a talk group address? The answer is absolutely nothing. There's a bit that's flipped on in the signaling sequence that tells the thing that receives it what it is. Okay, so it flips it on. Like if you're addressing a user, you'll have a 24-bit address for that user. If you're addressing a talk group, you'll be flipping on a group address bit, and the receiver will know that. Now there's the top addresses are typically used for Motorola. Now it uses the top 800 addresses. Okay, so it's best to stay away from those. It's also best to stay away from the top address, which is FFFFFFFF, FFFFFF, yeah. And that's an all call. That'll wake up everybody's radio, and it will start to beep on everybody's radio. So that is an all call. But Motorola uses the top 800 addresses for something internal to their systems. So if you were to use those, it could be, you could trigger something that you don't want to trigger, like maybe routing your call to something you don't want to route to. You could turn on recording. You could do all kind. You could disable something. There's any number of things that you can do with those addresses. So it's best kind of not to use them. But this is the addressing scheme, and again, you're under the control of the base station. There's many more. This is all I have really here. It's all I wanted to bring in. It's you're not going to be an expert in 40 minutes, but I could certainly try to answer any questions you have regarding this stuff.
Mark, I have a couple of questions.
Mm-hmm.
So you mentioned color codes quickly. You explained time slots, and I kind of understand that, but color codes are less intuitive. I'm not really sure. It's more difficult to understand what the purpose of the color code is. And my second question is about the different standards for D-Star and DMR. Are they different AMBI standards that are used between them?
Oh, you mean the vocoder or the standard?
The vocoder, yeah.
The vocoder is the same. It's AMB plus version 2, AMB plus 2. The actual standard of the protocol standard, what we're looking at in DMR here today, is completely different. I mean, there's different burst formats, different whatever. It's a closed standard.
Yeah. Okay.
You have to buy that from ICOM.
Okay.
Color code, it's something that hams really don't need to be messing with because we don't have the frequency, the super aggressive frequency radius that commercial systems have. There's another thing that's really cool that is part of the DMR standard now, and power control for the same reason, uplink power control. Color codes are kind of like PL codes, but what they do is there's an option on your mobile or on your portable to allow you to they call it roaming, quote roaming. What this allows you to do is it allows you to pick the signal that has the best bit error rate and grab onto that system. Now, you may be with aggressive frequency reuse. That means like you got 2 or 3 repeaters on the same frequency. They're technically they could be interfering with each other, but they're far enough apart where most of their users don't interfere, except at the fringe, where 2 repeaters might be able to hear them. So that's what the color code does: is it protects the one the unintended one. So you're set to color code 1, and the other one is set to color code 2, and you want to talk to the repeater that's on 1, and it's the repeater that's on 2 is not going to respond to you. It's not going to hear you. And in fact, the thing I was telling you about the advanced detection technique, where you peek up on you minimize the mean square difference between that sequence and what you receive, the training sequence. That helps you to receive the stuff that's desired. The other thing is that this leads into is the power control. So uplink power control, meaning the mobile or the portables can have its power controlled. And again, it's useless for hams because we don't pack our systems so tightly. But what they do in commercial systems, they put in this super aggressive frequency reuse. So all these stations on the same frequency or on the same 2 frequencies, and the base station receives you and sets your power to a target. So a bit error rate target. So it's just a range where it ratchets your power down many times a second and up. So if you get below that, your bit errors go higher than the target, then it's going to jack your power back up. But that's what that's for.
Thanks.
I got a question about the TDMA arrangement, Mark. I think I'm missing something fundamental here. According to the TDMA arrangement, you've got 2 time slots, 30 microseconds apiece or something. And those are per 12.5 kilohertz wide channel. That would suggest that you can only have 2 users actively transmitting or receiving from a specific base station at any given time. But that doesn't make a whole lot of sense, because presumably there are lots of users who are connected to a base station at any given time. Does a base station operate a whole number, like a bunch of channels? And if so, then do the mobiles connected to that base station channel hop in some way? Like how does that traffic management happen?
I see what you're saying. No, it's asynchronous. So when you're transmitting, you're connected on time slot 1, let's say, and somebody else is connected on time slot 2. They're talking to somebody else. You don't even hear them. Well, unless there's some weird bridge or something in the repeater, but usually that's not the case. Now, when you let up on your push to talk, someone else can talk, because they can request the channel, and the catch gives them access and right to transmit on that time slot. And then they release theirs, and someone else can talk. So it's just strictly mutually exclusive people transmitting on the same time slot, or somebody can be sending on the second time slot, but you don't hear them unless you're actually listening to it.
But it's already at least twice what you'd get on KSR or something, because KSR you can only have 1 person using it at a time.
Yeah. Except see, the difference between TDMA and analog is really that analog is commandeering the entire radio resource until they release it. TDMA is each user is commandeering the entire radio resource for half the time. To put this into more perspective, GSM is commandeering the 200 kilohertz radio resource for 8 slots or 16 if you're going half rate. So yeah, this resource is there. It's occupying this amount of RF bandwidth, but you're just sharing it amongst a whole bunch of people or 2 users simultaneously. And then you're mutually exclusively, push to talk, giving each other permission to transmit.
Okay, so if I had a half dozen users in my area that's served by a base station, they all wanted to use their radios at the same time, would that suggest that some 2 of them would be able to use their radios to transmit or receive at any given time, and the other 4 would be locked out until those 2 are done?
No, they wouldn't be locked out. They would be receiving. They could hear those people at the same time, just like a regular repeater. You hear them.
Couldn't we all be connected to different addresses though?
I see what you're saying.
Like, would I miss if Nick and I were both on the repeater at the same time, and I was listening to one address and he was listening to some other address, and I'm occupying the TDMA slot, let's presume there's some third user occupying the other TDMA slot, then does that imply that I'm transmitting and some other user is transmitting, so now Nick can't hear anything because there are no free TDMA slots?
That's right.
Twice as many as KSR or RBM then?
Well, so what it means, what it really means is if let's say you're on if you're on talk group, I don't know, 302, which is Canada,
yeah.
And Nick wants to transmit on 28112, which is Geneva,
mm-hmm.
and somebody else is on both slots. Well, either he's going to have to move to time slot 2 and put his on Geneva, or wait until time slot 1's available, because it's going to block the resource. You're going to be on 302, and it'll hold on to that resource for usually about 15 seconds.
Okay.
So yeah,
but again, there is some fundamental limit to the number of people who can occupy a base station at any given time.
Well, simultaneously, yes. But I mean, again, if you consider something like RBM, where you've got your IRLP, if I want to call into one particular IRLP talk group, I'm hogging the whole repeater while I'm doing so.
Yeah, exactly.
Come along and dial into a different IRLP reflector at the same time. Right? You can wait for me to finish, and then once I've dropped or whatever, I suppose you could butt in and force drop me. But if you want to talk to a different one, there's only one of us can be using that at a time. Whereas on DMR, we could both be operating in parallel on 2 separate time slots, as if there's 2 repeaters there for the price of 1.
Okay, yeah, but in IRLP though, the talk group per se is a property of the repeater or of the base station, not of the handheld, not of the operator, right? We set RBM to connect to a specific IRLP room. Is that true of DRM as well, or does every operator have the ability to connect to a different talk group?
Well, the operator, the network can, like DMR Mark, you need is quite a bit different than, well, DMR Mark was the first type of C bridges, the type of routers, and you actually had to add the talk group to the router. So if your repeater carries 302, then you could flip between 302 and other Canada talk groups. And normally the convention around here is the local or the nationwide talk groups, like the provincial ones, are on time slot 2, and the global ones tend to be on time slot 1. But that's not always the case, and it doesn't have to be the case. But yeah. But you can share. I mean, if you like Brandmeister, it comes up. You can bring up a talk group just simply by setting your mobile or your handheld to that talk group, and just bring it up. And now you get a route. The Brandmeister router routed it to you at that point. And now for the next so many seconds, you'll hear everything that's on that talk group.
Okay. Interesting.
So it's kind of cool. I mean, and there's loads of talk groups. I have friends all over the world, and I mean, that's why I do get on the Geneva talk group. there's a bunch of French talk groups and stuff that, just old friends of mine, and the Illinois talk group I show up on once in a while because I'm originally from Illinois, which is filled with former Motorola people. Yeah, so it has nothing to do with officially the location or anybody owning those talk groups. They're just addresses, and you can use them.
Mark, can you explain a bit about uplink versus downlink? I mean, on something like one of the FM repeaters, KSR, RBM, whatever, we've got different frequencies for the, to the repeater and from the repeater. Is that still the case with DMR as well, or is that built into the time slot type thing? Do you have a time slot for uplink and a time slot for downlink, or taking turns with the uplink and downlink in those time slots, or is that still a frequency division thing?
I know what you're thinking. It's still frequency division, multiple access.
Okay.
I mean, frequency division multiplex. So you're thinking of TDD, which was the Japan standard for cellular, was time division duplex. That's where you have a period of time for uplink, a period of time for downlink. There's no duplexer needed, and but of course it uses capacity to do that. And there's a lot of complications and a lot of quirkiness with the transmitter and the spectral mask and the spectral occupation, and just a lot of weirdness. So it tends to work.
Fair enough.
Better to use the frequency division duplex.
Fair enough. But presumably in that case, I'm still, if I'm transmitting approximately half the time, I guess slightly less than half the time on one transmit frequency, I assume I'm still receiving on the other receive frequency, at least enough to find out whether I'm still in the time slot or whether I've drifted off. I get some like time slot correction thing to say, yeah, you can carry on transmitting, you're in your time slot, you still got time slot 1, keep going.
Yeah, the cache is still telling you got right to transmit. Now, if you get too weak to copy, you go beyond the bit error ratio threshold.
Right.
You won't get a cache burst that says you got the right to transmit. In fact, let's see, I can show you let's see, we'll go over to Kitchener. So Kitchener repeater, and let's see if I can bring up. I'll just bring up the local one on time slot 2. See, that little tone meant that I got the catch, I got the right to transmit there. Now, if I mess up the propagation, well, it still got into it. But anyway, if I didn't get the right to transmit, it would give me a tone that goes and it would say on the screen, the resource is busy or the channel is busy.
And that would be if either the channel is being heavily used and so there's no time slot available, or if your bit error rate is bad and so you're not going to be able to get enough data.
Yeah, if you're too far from a site or your bit error rate's bad, the Kitchener repeater has got good coverage. That's a DMR Mark network.
Mm-hmm.
It's not a Brandmeister network, but some of the stuff's bridged. So you could hear Ontario Talk Group. They're bridged together. That at least I remember they've been bridged together. I think they're still bridged together. But yeah, it's pretty cool. But you'll hear. I mean, if your talk group is busy, you'll hear your talk group on that time slot. You'll hear it. Now another trick you can do I don't know about all DMR equipment, but because these addresses are just addresses, right? I have a time slot. I have a position on the. Let's see. I don't know if you can see it, but there's the channel selector. So channel selector 1 position. I have it set up so that it receives multiple talk groups. It receives a whole bunch of them. And it also, when it receives one, it locks the radio resource there for 20 seconds. That's just what I set it to. So I don't have to scan. I don't have to, mess with the, I can, if Geneva comes up and something else comes up, I'll hear it. But if Geneva comes up and Ontario comes up at the same time, I'll hear Geneva. I won't hear Ontario because Geneva had won. They won the race to commandeer my resource.
Okay, so that'd be similar to my scanning through all of the local repeaters on my FM radio, and
exactly.
my radio just locks to a repeater that comes up for the next 10 seconds or something.
Exactly the same.
And respond, then that's okay. Otherwise, it'll proceed.
It's exactly the same.
Right.
But but anyway, that's hopefully. I don't know what else might be something you're wondering about, but if you have any questions, certainly let me know. And send
Let
it.
us see. I know Nick and Jonathan have had a good chance. Is there anyone else with questions for Mark on DMR? Indicate in some way, either raise your hand or do the Zoom hand raise under reactions so I can tell if there are any other comments or questions. And certainly the discussion doesn't have to end tonight. Mark has become a regular on our nets on the VHF, on our RCK or KSR. And actually I've heard him on HF bands as well. And I'm sure anytime you'd be happy to have a chat to follow up on some of the things that have been raised tonight. So any other comments or questions from anyone else in the room?
I'm going to stop. There we go.
There we go.
If no one else does, I got one more.
Okay.
Go for it, Nick.
So I was going to ask, this is all everything you've described is all very repeater controlled and coordinated. I was wondering whether this is any use whatsoever simplex if you're away from repeaters and things in the sticks.
It works really well. DMR works super well on simplex. Now, your receiving station doesn't control you. I mean, it doesn't give you a catch or anything like that, burst. You basically set these things up so they transmit when you hit push to talk. But oh man, simplex DMR works like super well.
So you're not waiting, you're not being controlled, you're not waiting for ratchets and things, you're just transmitting for 50% of the time, person on the other end's picking you up for 50% of the time, decoding it, listening to it, I guess.
Yeah. No, one thing I have to tell you guys, I completely forgot, but I just did this. This radio here is 10 years old, 11 years old now. Motorola equipment always looks like it's new. Last week, I started to have some weird problems with some bit errors on transmit on that particular one. So I loaded up my turbo tuner software on my other computer and plugged it into this thing. And it was 500 hertz too low. So the lesson here is that DMR is extremely sensitive to being off frequency. So I guess every 11 years you must recalibrate your transceivers, but I did, and of course I put it on my frequency counter, which is sitting back there, and Turbo Tuner adjusted it so that it put a dead carrier out at a certain frequency. So once I have a calibrated frequency counter there, and I could get it within a few hertz, and it was okay.
Cool stuff, thanks.
All right. Any other final questions or comments? If not, Mark, on behalf of the club, we really want to thank you for sharing. I know this is something that you certainly have been passionate about, and some of the comments that are in the chat allude, we think it's complicated, but maybe not quite as complicated as we think it is.
Yeah, I hope it helps people
And the
somewhat.
basics.
Yeah, I hope it helps people somewhat. And
Yeah.
you'll see more and more of this type of stuff as we go forward in ham radio.
Well, and I think there is interest in the members, some members of the club in terms of doing more work on the digital side, and certainly and using DMR. And so I think we will continue to learn and grow and develop that as well. So thank you so much, Mark.
Thank you, guys.